Welcome to this explainer. Let's dive right into one of the most fascinating paradoxes in all of nuclear physics. Today, we're climbing what I like to call the energy mountain of the universe to understand exactly where our most powerful energy sources come from, and more importantly, why we use the specific materials we do to power our modern world.
We're going to tackle a really brilliant question that honestly gets right to the heart of how nuclear energy actually works. Think about this for a second. Why do we talk about the fission of incredibly heavy, rare nuclides, like uranium, rather than nuclides in the mass region of iron? Iron is literally everywhere. It's strong, it's stable, and looking at the physics, it actually seems like it has a much higher energy in store. So why aren't we just splitting iron to power our cities?
Well, to solve this little paradox, we have to look at a fundamental, incredibly powerful concept called binding energy. You can think of binding energy as the ultimate cosmic glue. It's the exact amount of energy required to completely break a nucleus apart into its basic building blocks, protons and neutrons. And conversely, it's the exact amount of energy released when those pieces bind together in the first place. Basically, the stronger the glue, the tighter the nucleus is bound.
And this maps out beautifully onto the curve of binding energy, which is essentially that energy mountain I was talking about. If you start way over on the light side with elements like hydrogen and smash them together, which is fusion, you climb rapidly up the steep side of the mountain, releasing massive amounts of energy. That's literally how stars shine. On the flip side, we have the super heavy boulders like uranium. By splitting them apart, which is fission, we roll down the other side of the mountain, and that also releases energy. Both processes, fusion and fission, are basically just trying to reach the top.
But what's sitting at the absolute undisputed peak of that mountain? Iron-56. Iron-56 has the highest binding energy per nucleon of anything in the universe. It is the most tightly bound nucleus that exists. You can think of it as the ultimate cosmic ash of star creation. Once a massive star fuses elements all the way up to iron, the star physically cannot squeeze even a drop more energy out of the fusion process.
So here is the crucial takeaway. When we say iron has the highest binding energy, it doesn't mean it has extra energy in store just waiting to be released, like some sort of battery. Actually, scratch that, it's the exact opposite. It means its protons and neutrons are sitting at the very bottom of the deepest energy well possible. If you want to split an iron atom, you actually have to pay a massive amount of energy just to break that cosmic glue. But a heavyweight like uranium-235, it's further down the slope. By splitting it, its fragments move up the curve toward iron, and in nuclear physics, moving toward iron releases the difference in that binding energy. And let me tell you, that difference is absolutely staggering. When we split just one single uranium-235 nucleus, the binding energy of the pieces shifts from about 7.5 mega-electron volts per nucleon to 8.4. Now, a 1 MeV shift might sound kind of small, but when you multiply that across the entire nucleus, you get a supercharged release of about 200 mega-electron volts of total energy per fission. To put that into perspective, burning a single atom of carbon in coal gives you a measly 4 electron volts. Splitting one uranium atom, 200 million. Now, nature doesn't just hand over this energy for free. These heavy nuclei don't just casually split in half effortlessly. They're held together by the strong nuclear force, which acts kind of like a liquid drop, keeping the whole nucleus nice and spherical. Before they can split and roll down the energy mountain, they face an energy barrier. It's like a little hill you have to push a boulder over before gravity takes over. For a heavy element to actually split, it needs a little extra push, an excitation energy. As it absorbs that energy, the perfectly spherical nucleus begins to deform. It stretches out, looking almost like a peanut or a dumbbell. And once it stretches past a critical threshold known as the saddle point, the electrostatic repulsion between the protons violently snaps the nucleus right into two pieces.
So how exactly do we give it that push? We throw a neutron at it. But there's a massive difference in how different isotopes react. Take uranium-235. It is incredibly special. When it captures just a slow, low-energy thermal neutron, the nuclear restructuring happening inside releases about 6.5 MeV of energy. That is more than enough to cross its 5.7 MeV fission barrier. But then you have uranium-238. When U-238 captures a neutron, it only releases about 4.8 MeV internally. That is just not enough to get over the hump. U-238 absolutely requires a high-energy, fast neutron to literally smash into it and provide that missing threshold energy. And this quirk of quantum physics creates distinct categories for our reactor fuels. First, you have your fissile materials like U-235 and plutonium-239. These are the holy grail because they cheerfully split with neutrons of basically any energy, especially the slow ones. Then you have materials that are fissionable but not fissile, like U-238, which demand that high-energy, fast neutron. But U-238 has a secret superpower. It is fertile. If U-238 captures a neutron and doesn't split, it undergoes beta decay and literally transforms into a completely new fissile element, plutonium-239.
That distinction is a real game changer because of what happens next. When a fissile material like U-235 splits, it doesn't just release energy. It spits out 2 or 3 brand new secondary neutrons. And because fissile materials can be split by these secondary neutrons even after they've slowed down, they trigger a beautiful, bouncing, self-sustaining chain reaction. One split causes 2, which causes 4, propagating through the reactor and giving us a steady, reliable stream of immense power.
But here's where the physics gets incredibly weird and honestly kind of wonderful. When that heavy nucleus snaps, you'd intuitively expect it to break perfectly down the middle into 2 equal halves, right? Well, wrong. The mass distribution of fission fragments almost always creates this asymmetric double hump. Instead of one big spike right in the middle, you get a group of lighter fragments and a completely separate group of much heavier fragments. Why on earth does it do that? It all comes down to a fascinating quirk of quantum shell corrections. It turns out even in the violent, chaotic split of nuclear fission, nature is still desperately seeking stability. The heavy fragment group almost always centers around an atomic mass of 132. Why? Because of an isotope called tin-132. Tin-132 is what physicists call doubly magic. It has fully closed shells of both protons and neutrons, making it exceptionally stable. The nucleus literally prefers to tear itself apart asymmetrically just to create fragments that are as close as possible to this super stable magic number.
So, because we absolutely rely on these quirky, complex heavyweights to generate power, since, as we learned, iron just won't do the job, engineers have had to develop some seriously brilliant advanced fuel cycles. We've got systems like the CANDU reactor, which efficiently uses natural, unenriched uranium in a once-through cycle. We have mixed oxide or MOX cycles that cleverly recycle the plutonium-239 we created from our fertile U-238. And looking to the future, there's the thorium cycle, breeding superabundant thorium into fissile uranium-233, vastly extending humanity's clean energy resources and squeezing every last drop of value from the very top of the periodic table.
It really is an incredible journey. We started with the paradox of a single stable iron atom, and we climbed all the way up the energy mountain to understand exactly how splitting the heaviest, most unstable boulders on Earth can safely and cleanly power entire cities. So, I'll leave you with this to wonder about. As we master new fertile fuels like thorium and continue to innovate our reactor designs, what new boundaries of the energy curve will we conquer next?